Right, welcome everyone for the third edition of Astronomy on Tap London Live, or as we should call it, Astronomy Off Tap. As you know, pubs are still closed across the country, but we are still bringing you the science and the astronomy and to you. And we want tonight to discuss two topics with two amazing speakers, and I think Chiara will introduce them fairly quickly. Chiara?
Yes. Hi, everybody. So the first speaker tonight will be Dr. Amelie Saintonge. She's an associate professor at UCL. But yeah, Amelie, you're very involved in outreach activities as well. Do you want to tell us about what you're up to at the moment?
Yeah, but at the moment, a lot of things are obviously on hold, but I do these days, I particularly like to enjoy exactly like this with sort of the general public, not necessarily the typical crowd you see when you go to science events and all that. So this is right up my alley.
Perfect. Yeah, and today she will talk about the science behind supermassive black holes. The second speaker is Professor Alan Aylward. He's an emeritus professor at UCL, now retired, and the main interest is atmospheric physics. And today he will talk about exoplanetary atmospheres.
All right, thank you, Chiara. So during the week, Corentin, our Twitter guru, has sent questions. Some of them will be in the talk, some of them won't, so pay attention if you want the answer. Before we start, I have to remember it's supposed to be, an event that should have been in a pub. So, take some drinks, take some snacks, make yourself comfy at home, and get ready for the science. Another thing is that we have a 20-second delay. So if you can already ask questions on the chat during the talk, we will then select them and we will follow up the 15-minute talks by about 15 minutes of questions. And you can ask questions and get follow-up questions. All right, so maybe we can start already with your talk, Amelie.
All right, there we go. Slides are coming. All right. Well, so I want to talk to you about supermassive black holes, not just any black holes, supermassive black holes. The picture we have on the title slide here is, possibly the most famous black hole out there. Unfortunately, it's not a real one. It's a fictional one. Some of you who are fond of the movies probably recognize it as the supermassive black hole in the movie Interstellar. And while this is just Hollywood, it is actually a super realistic simulation of what a supermassive black hole might look like if we had the chance to go up near and close to one. Although, as we'll discuss soon, that might not be a very good idea. So before I talk about these supermassive black holes, I just want to bring in a bit of sense of reality. So this is the Hollywood image. We're lucky these days to actually have an image of what a black hole actually looks like. And that's an image that's fresh from just about a year ago. And so you might have seen this picture in the news, right? This is an actual image of a black hole, the dark stuff at the center of the donut. So hopefully by the end of the talk, you might have a bit of a better understanding of A, what that image is, B, how we got that image, and see why it's actually absolutely mind-boggling that we're able to see this. And I remember when this came out in the news, a lot of the public said, well, that image, well, it's a bit rubbish, isn't it? Which, as an astronomer, you look at this and you just realize how amazing it is. So that's kind of what I want to convey to you today. Like, why is this so awesome? So first thing, black holes, what are they? Well, in their simplest form, black holes are actually something that are relatively easy to wrap our heads around. So black holes, small black holes, are just the end product of the lifetime of massive stars. So what I'm showing you here is just a diagram showing all sorts of different stars, right? So stars are born in gigantic clouds of gas and dust, and you will form a bunch of small stars and bigger stars and very, very big stars. So the very small stars, things a bit like our sun, end their lives as white dwarf stars, whereas the very, very big stars towards the end when they run out of fuel to do nuclear reaction, they collapse onto themselves. And there's absolutely nothing to stop gravity from just bringing all that stuff right down to a single point, which we call a singularity. And that's how you get a black hole. I'm glossing over a lot of the physics, but that gives you the general idea. So if you take something like the sun, something that has the mass, a star like the sun, right? And for comparison, I'm showing you the solar system. So Earth is there, so that's the sun to scale. If you take a star like the sun, and if you were to collapse it to something like a black hole, in comparison, it would become this big. I put it on the map of London to give you a sense of scale. So you would have the entire mass of the sun compressed in the region as, just a few kilometers across like this. So incredibly high densities, gravity is incredibly strong. So that has all sorts of weird effects that we're trying to understand better. Right. Enough about small black holes. What I want to talk about really is the really big ones. So supermassive black holes are known to exist at the centers of most galaxies. So most of the big galaxies we know and where we've looked, we have found supermassive black holes at their cores. And one of the big questions in astrophysics is to figure out how they get there. How do we get these enormous monsters right at the center of most galaxies? So I've shown you how it's actually pretty easy to make small black holes. You take a star, you let it age, and then you let it collapse at the end. Then after that, black holes, one thing we know about them is that they're really good at attracting stuff towards them because of all their gravity. So what the drawing here shows is a black hole at the center and the stuff around it, which we call the accretion disk. So you get a lot of material, gas, dust that kind of spins around the black hole. And then you can imagine some of that material falling into the black hole, which would feed it and make it increase in mass and size. So in principle, you could think, oh, this way I could start with a small black hole, make it feed and then grow it into a supermassive black hole. The problem with that is that black holes are a bit like messy toddlers, right? You put food in front of them, they try to eat it and then more food goes in their face or on the floor than in the mouth. Black holes are a bit like that. There's a limit to how much stuff you can cram into it before they start burping it all out. So that's not a really good way to grow black holes. So there remains the question, so we have these small black holes and we know about these supermassive black holes. How do you go from one to the other? And that, which seems like a very simple question, is actually a huge problem in astrophysics these days, right? So if you look at the range, so the numbers you have, the mass scale, these are logarithmic scale, which we're kind of getting used to these days. So we have lots of stellar mass black holes that have sort of the same mass as the sun. And then we have these supermassive black holes that have millions of times the mass of the sun. And as of now, we have no evidence for any black holes with masses in between that range. So black holes come in small and in XXXL, but no sizes in between as far as we can tell. So that is still kind of a really big challenge for astrophysics to try to reconcile all of that. There's another issue with these supermassive black holes is that not only they're super big, but they seem to appear very early on in the history of the universe. So what I'm showing you here at the bottom is sort of just a cartoon of the history of the universe. So you have the Big Bang on the left, and then time goes on to the right. So we'd be here at the right of the screen. The first stars and galaxies start to form about 400 million years after the Big Bang, so somewhere around here. Thing is that as of now, we have observed already supermassive black holes with masses millions of times the mass of the sun. Really, really less than 1 billion years after the Big Bang, right there in that very early phase of the universe. And that again is really a challenge for us astrophysicists to kind of try to piece together, how do we form these super beasts that quickly? And how much of an impact they can have on the universe around them. So this is actually a super active area of research at the moment. Some people on the line at UCL are actually actively working on these kinds of questions. So the kind of stuff I'm talking to you about today is really at the forefront of kind of what we think about in day-to-day research. So I've told you about black holes in general, some of their properties. I'll just dig a little bit more into, what are their properties. And in some sense, for all the mystery that enshrouds them, they're actually relatively simple objects. So when we think of the black hole, what we actually want to mean is the singularity. It is that point of essentially infinite density, that minuscule region of space where you're able to cram all of that mass. So that would technically be the black hole. What most people then would actually mean when they talk about the size of the black hole is this circle here, which I'm showing you, which is what we call the event horizon of the black hole. And the event horizon is the furthest, the closest you can get to the black hole and have a chance to, go away and live to tell the tale. If anything gets closer to the black hole than the event horizon, it's gone. Right? You're just going to stay trapped into the black hole. There's nothing that can escape the gravity. So effectively, that's the edge of the black hole. However, there's nothing special about this. If we were an astronaut, if we were to fall towards a black hole, you would cross the event horizon and not notice whatsoever that something as dramatic as, crossing the event horizon of a black hole would have happened. That's this fundamental thing about general relativity when they describe black holes, that there's nothing special about the event horizon. It's just the point of no return for light. What's also cool and special about black holes is that they're very simple. You can describe any black hole with just a combination of 3 numbers: the mass, how much it weighs, the spin, which is a description of how much it rotates, and the charge, if it has electric charge. If you think about this, is really, really simple here, right? If you think about anything in real day life, like I have let's say I have a mug here and I have my phone, right? They both have roughly the same mass. I can make them spin at the same rate, let's say. But if I wanted to describe what they are, I'd need a lot more numbers. I'd need a lot more information to describe what they are, right? Whereas black holes, only 3 numbers describe them. And that's that sort of paradox about black holes is something people have coined the no-hair theorem. The sort of story of that term is sort of a bit strange, but so when people talk about black holes and the no-hair theorem, it's that idea that you can uniquely describe a black hole just by this combination of these 3 numbers. So let me ask you a quick question before we go on. I've talked to you about small black holes, big black holes. Now, let's say we had a special rocket ship where we could travel infinitely fast and go to study one of these black holes very close by. So my question to you is, which one would you go to see? Which one is our best bet if we want to find out more about black holes? The criteria here is we want to survive for as long as possible. Right? We want to be able to get as close to the black hole as possible before we are torn to shreds, which will happen regardless of which of the black holes we go to visit. So which one do you think? Which one we stand a better chance of getting close to? I'll let you think about it for a second. Come up with your answer. Yes, the answer is, perhaps surprisingly, the big black hole. Right? The big black hole, that might sound a bit counterintuitive. The big black hole is very massive. It has very strong gravity. The thing is that the gravity acts on very long distances, right? So what will shred you to bits if you go to close to a black hole is what we call tidal forces. It's the difference between forces on different parts of your body or your spaceship. So imagine you're falling feet first into a black hole. If you go towards a small black hole, it will pull on you, but it will pull on your feet stronger than it pulls on your head. And that will lead to a stretching, which we have a scientific word for when we talk about black holes. We call that process spaghettification. Whereas if you go towards a supermassive black hole, yes, gravity is stronger. It will pull on you stronger, but it will pull on you all in one go. So you'd be able to get a bit closer to the supermassive black hole, which is why if you've seen Interstellar, the whole premise of going to a planet close to the supermassive black hole is not all that crazy. All right. Now, I've told you about black holes like that. You've very kindly taken for granted that, I'm telling you something that's sensible, but I've shown you no evidence as of yet that black holes actually exist, apart from that image I showed you at the very beginning. So I'm going to show you a little video here for what I think is the possibly, until that image came out a year ago, was the best evidence we had for the existence of supermassive black holes at the centers of galaxies. I'm going to start this video. So this is an image of our own galaxy, the Milky Way. And what we're doing right now is to zoom towards the center of the galaxy. So these are all real images stitched together. There's no CGI anything here. So we're zooming in towards the center of the galaxy. Around this point, we're going to switch from optical to infrared light, because that will allow us to see through the dust that's kind of enshrouding the central region of our galaxy. So that happens around here. So we're going to continue going towards the center and continue. That's when you realize that the galaxy is a very, very big place, lots of stars. Okay, we're almost to our destination. Now we're at the very center of the galaxy. I'm going to pause it for a second here. So what we're going to see now is a video. It will move. So what this image, all these dots, this is an actual image of the very, very central region of our galaxy. All of these white dots are actual stars at the center of the galaxy. And people have been measuring this, looking at this region for a couple of decades, and taken pictures periodically over these 20 years and stitched them together in a little movie. So this is what I'm going to show you now. So keep an eye on some of these stars. Again, real data taken over a period. Look at this thing here, this star here. Do you see how it's moving? But it's not moving randomly. You can see how it's kind of tracing an orbit, but an orbit around seemingly nothing. Right, so if you've done any kind of basic physics, GCSE level, we'll have to learn about, Newton's theory, orbits, basic physics. We know that when something is in orbit, it's in orbit around something. There's something in it to keep it on that orbit. And because we know that basic physics quite well, we can calculate, okay, I have this star, I measured the period of this rotation, a couple decades. I know how far it is, I know how massive it is. I can figure out what's that invisible mass at the center that's making all these stars move the way we see them. If you do that calculation, you end up with a number that's about, a few million times the mass of the sun. So you have something that's a million times the mass of the sun in a very small region of space, and that has a very high gravitational field. I mean, if that's not essentially the definition of a black hole, I don't know what is. So that's really, people might say it's a bit indirect, but it's still very good evidence that we have these supermassive black holes at the centers of galaxies. So just to tell you, really to tell you as well a little bit about, how we got that famous image, the donut-looking image. So this image I just showed you, this movie, was taken with a telescope in Chile called the Very Large Telescope. If you look at here, you will see it's just the technology. I don't have time to go into the detail, but you essentially have to shoot a laser to the sky to create an artificial star and track the brightness of that star and the subtle twinkling it makes to be able to correct your images to make these pinpoint sharp images of these stars at the center of the galaxy. This is just astonishing technology. The fact that we're able to build these machines to take these images is really, really, really extraordinary. So to go one step better, what people have done at this observatory is to have not one, but 4 of these telescopes, these very large telescopes, and Very Large Telescope is the actual name of these things, and to have them connected and work all together using an instrument here called gravity that connects the light from all these telescopes to make one image. So essentially you're taking multiple small telescopes to simulate one really big telescope. And that process is called interferometry. And if you want to do it well, you need to space out your telescopes as much as possible to be able to simulate a big telescope. And the biggest telescope we can simulate has essentially the size of the planet when we stretch our telescopes across the globe. So this specific map here I'm showing you highlights the position of several radio telescopes that work all together to form something we call the Event Horizon Telescope. This is an example of one of the stations that's part of this setup. It's in the Atacama Desert in northern Chile. So to make this image of the black hole, people had to take the data from all these radio telescopes all across the world, make sure the timing was absolutely spot on for them all to take the data at the same time. Then that data was flown to a central center where it is all combined digitally. To do that is an incredible amount of computer. You need massive supercomputers to do this. You do that carefully. It takes years to crunch all these numbers and get it right. And then at the end, you have hope of getting a picture of a black hole. So this is what happened about a year ago, right? We heard there was an announcement that it was going to be a press conference, first result of the Event Horizon Telescope. All astronomers got really excited. We knew what was coming. We knew it was going to be a picture of a black hole. Maybe, I think we didn't really expect the interstellar type image, but what we got was this, which was actually exactly what people were expecting. So, when you think that to make this image, we essentially had to turn our entire planet into a telescope, I think it's pretty fascinating, right? That we can build these telescopes to take this image, I think is pretty fascinating. So what we're seeing here in this image, at the center, the singularity is this. This dark shape is roughly the size of the Schwarzschild radius. It's 3 times the Schwarzschild radius, which is the radius of the black hole. So it's kind of the event horizon of the telescope. It's the bit, so any light that's trying to come from us is being stuck. It cannot escape. The shiny bit you see around it is this accretion disk, this material that's rotating around the black hole. And the light of that is being bent by all the gravity. So you get multiple images of the same bits of the accretion disk in different places because light kind of goes and circled around the black hole. And the fact that it's lopsided, that you have one bit that's brighter than the other one, it's because this accretion disk is rotating. So part of it is going towards you. So it's kind of being boosted. It looks brighter because it's like going straight at us versus the bit that's receding further away. So I think, when we think about black holes, so we have, the physics of it, the fact that black holes were essentially at first just a mathematical construct. They emerge out of the equation of general relativity, which you can solve, and then you find as a mathematical solution to these equations, something that is a black hole, which at first we thought was just an impossibility. How could there be something as crazy as something that has like a crazy amount of mass in an infinitely small amount of space? That just doesn't sound possible. But these things are out there, which is surprising in and of itself. But then the fact that we're able, to have the science to comprehend these things, the ability to build the machines, all over the world to take these images is equally fascinating, I think. I don't know which of these two things, I find more impressive. And then looking forward to the future, the next frontier is to use not light, but gravitational waves to study these supermassive black holes. That's the big thing. And to do that, we're pushing even further what we can do. We're talking about building things in space, orbiting the Earth, millions of kilometers apart, to be able to detect infinitely small signals coming from colliding black holes in the distant universe. So this is only the beginning, really. I think I gave you a sense that there's all these open questions, lots to figure out still. So stay tuned. Black holes haven't finished telling us all their secrets.
All right, thank you very much, Amelie. That was an extremely interesting talk. And we can, I think, start with questions. So it's going to take a bit of time from YouTube questions. But maybe from one of us, Chiara, or...
Yes. So Amelie, you mentioned that these supermassive black holes grow by, eating the gas surrounding them, and also you showed the images of our own supermassive black hole at the center of our galaxy. So what's like its level of activity? Is it, eating gas? What is it doing?
Yeah. So they go through phases. These supermassive black holes. The one at the center of our galaxy is taking a break. Let's say it's in between meals, so it's having a snack once in a while. So once in a while you'll have a small pocket of gas that will fall in. It's something that was studied quite a lot recently. We actually saw a cloud of gas going really near, going in on an orbit really as close as possible as you can without falling in, being stretched out of space. It just escaped it, but yeah. So our own Milky Way black hole is it's a bit quiet at the moment, not indulging too much.
Right. Do we have other questions? Quentin, maybe?
Yeah. What would happen if say a star would fall on the supermassive black hole at the center of our own galaxy? What would happen to us?
What would happen to us? Well, to our own survival, nothing much, right? So that these certainly the supermassive black hole at the center of our galaxy is very, very far from us. So if you try to think of the galaxy, we're sort of on the outer edge. Maybe in the movies and things, we think of super black holes as something that's like a vacuum cleaner that actively sucks things from far away. I mean, that's not really the truth. They're really powerful, but their sphere of influence is relatively small as well. So certainly from our perspective on Earth, we're very safe from the black hole, even if it were to, get a big meal and some other poor, unfortunate star were to fall in.
Right. So we have, so the chat is catching up. We have a first question from Stephen. Sorry. How can we measure the spin of the black hole?
That's tricky, and we actually haven't done that very much. So, for example, this image we have of this, if we were able to take these images, we could tell the difference. This donut would look different if the black hole were spinning or not, or spinning at a different rate. So we could tell in ways. Now that we can actually look at these black holes, there's a possibility to actually tell.
In the meantime, there was also another question. So what happens to objects that go in a black hole? Okay. Yeah. The question disappeared, but yeah.
Yeah, and that's a really good question. So in principle, if something goes in, it's being just added to the overall mass of the black hole, right? Remember I told you that there's only these 3 numbers, right? So if you chuck something in the black hole of a given mass, it adds to the total mass of the black hole. It will fall into the singularity at the middle. What actually happens there, then who knows? I think we do not have even the mathematics or the physics to actually describe what would happen there. Perhaps we have the imagination. I'll leave that to the science fiction writers maybe to come up with an answer. But it leads to another interesting problem, which is something that might seem trivial, but that is a fundamental crisis in physics, which is this fact that it's only these 3 numbers, right? If you put different things inside a black hole, the only thing it remembers, it's the total mass, right? If I go back to my example, so if my mug goes in or my phone goes in, the only thing I can tell after that, I will observe the mass of the black hole growing by a few 100 grams, but that's it. I will have no way of knowing if it's a mug or a phone that has gone into the black hole. And that's huge, right? You've probably heard of things like energy conservation or angular momentum conservation. They're basic laws of physics. There's also something in physics that's information conservation. You're not meant to be able to lose information. So the fact that black holes can seemingly erase information is actually a huge, huge problem. So there's a lot of push to actually understand from a theoretical physics sense what actually happens to stuff inside a black hole. Is it really lost forever in terms of all these other properties? So really good question. We don't really know, but we're working on it, in short.
Right. So I think very fittingly, the last question is on the charge. So, how does a black hole have a charge? And also, does this mean there are black holes that are neutrally charged?
I think as far as I know, we have no evidence of that whatsoever, right? It's a possibility. It's, again, these kinds of things that are allowed by the mathematics, but we don't know. So as observers, there's no way we can tell at the moment. So that one remains to be seen.
Okay.
Yeah, so it shows how bad it is, right? There's 3 numbers, and we only really have a good handle on one of the 3 numbers. So we won't be out of a job soon.
Right. I think it's a great conclusion. We will stop here. Thank you again, Amelie.
My pleasure.
We will now move on to Professor Aylward for a talk on exoplanetary atmospheres. Right, Alan, if you can share your screen. And in the meantime, I have to give a shout out to UCL Physics and Astronomy, who are, giving us a bit of money to run this, well, actually paying the Zoom account. So thank you. Thank you for doing this, bringing the science out there safely. Right, Alan, are you ready? You're muted. Right, okay, now you're unmuted.
Okay, I've got to find it first. Well, it's in here somewhere. Okay. Can I share that? Yes.
Right, excellent. Okay. Well,
okay,
let's go.
Well, there's obviously a number of topics that fascinate the public in science, and we're hearing about 2 of them today in astronomy. One of them is black holes and cosmology generally, but the other topic that's grown in recent years is this idea of planets around other stars. Now, the reason, of course, that we're interested in that is it goes back to the fundamental interest that mankind has always had is there other life? Is there other life out there? And part of what we're interested in other planets for is to find out whether there is life elsewhere. So that's always fascinated man. And the first sort of questions that we ask are restricted to our own solar system. And we tend to be very parochial in our search for life. The question we ask has to be directed around some way of looking for it. And we always seem to come back to water. So the question is nearly always in which environments is liquid water exist? Because as far as we know, on Earth, all life relies to some extent on there being liquid water. So in our own solar system, we look for places with that, and we find out, for example, that Mars once had oceans. So we ask the question, could Mars have had life earlier in its history? And we have probes on the planet at the moment looking to see if they can find evidence that that was true. There are other planets or other places in the solar system where liquid water exists. Surprisingly, way out, Jupiter and Saturn, their satellites, which are wrenched by tidal forces, get heated up so that what should be ice so far out ends up being heated up to form liquid water. So we know there are oceans on some of these satellites out there. And the question, of course, is if they've existed long enough, could life exist there as well? At the moment, though, we have no evidence for any other source, even within the solar system. So let's cast our net wider. And there are lots of other places in the universe we can start looking. In our own galaxy, there are 400 billion stars. There are 170 billion galaxies out as far as we can see to 13.8 billion light years away. So there's a lot of places where there are stars. And if only a small fraction of those had planets, and if even a small fraction of those had good conditions, that still leaves a lot of places where, in theory, life could develop. So where are we looking at there? We're again using this same question about water. So you will have heard of this idea of the habitable zone, or the Goldilocks zone, as some people call it. And that's based purely on the idea that we're looking at areas where liquid water could exist. So if we take our own solar system as we have here, the planets going out, here is Earth sitting here, Mercury, Venus and Earth. We're sitting in a zone which is where life can exist. And the calculation is quite simple. You take the sun, you know how much energy comes from it. You see how much of that energy is reflected off the planet. That tells you how much is absorbed, what the temperature of the planet should therefore be. And if it's between 0 and 100 degrees Celsius, then liquid water can exist. So we have a zone beyond that where it's too cold, and in this region, its water is going to be in the ice form. We have a region inside that where it's too hot and it's vaporized, and so we have this nice pink zone in the middle where the Earth exists in this habitable zone. Of course, that's very simplified, and in fact, if it wasn't for the greenhouse effect, Earth would not actually have a liquid surface. We would have an ice-covered surface. So you can thank the greenhouse effect for the fact that we do actually have oceans. And also, I've also pointed out that even out here, Saturn and Jupiter have satellites where liquid water exists. So this idea of a habitable zone is very simplified, but we have to start somewhere. So we use that as the basic criteria. And we look at other planets around other stars. And here we have a list of stars in size. So for example, here's our sun. These are the planets going out for the sun. And the habitable zone is this green region here. These stars are bigger than us. These stars are smaller than ours. As the stars get smaller, they become dimmer, and therefore the habitable zone moves closer to them. If you go out further, if you get bigger stars, then the habitable zone goes out further. But this gives us a roadmap. This tells us what we're looking for around any other star if we're looking for a habitable area. That, of course, means we need to find that there are other planets out there. And the question is, are there? And until 1995, we didn't actually know the answer to that. In 1995, we had this defining moment where the very first observation was made. So we were looking at a star called 51 Pegasus, looking at the spectral returns from that. And in this particular spectral line, for example, we noticed that this emitter was, the spectrum was going up and down in frequency. So what does this mean? Well, this suggested that whatever was emitting was moving towards us here and away from us here, and then towards us again. So this is a star that seems to be wobbling backwards and forwards. So how do you explain that? The only way you really explain that is by saying that there must be a big planet going around it, and that big planet is causing it to wobble backwards and forwards. So we have this information, and the curve actually tells us quite a bit. So the amplitude of the curve, for example, tells us how big the planet is. We know how big the star is, so how big it wobbles is dependent on the size of the planet. The period of this tells us the orbital period of the planet, so we know how long it takes to go around the star. So what we have here is a measurement that tells us how big the planet is and what its orbital period is. And in this first instance, the amazing thing was that we have a planet the size of Jupiter going around the star in 4 days. So it would have been well inside the orbit of Mercury in our own system. Very, very strange system, controversial at the time. But what happened, having discovered this, is the floodgates opened. Suddenly everybody and their dog wanted to find exoplanets. And so they were all out there looking, using different methods. This method was used by a lot of them, but then another method was found, and that was to use a thing called transits. Now, we all know in the solar system what a transit looks like. This is a Venus transit. So here is Venus crossing the surface of the sun. This little black dot is Venus. And you can imagine that what this means is that when Venus is in front of the sun, some of the light from the sun is cut off. And so you can take this to exoplanets, to other planets, and say, if you have a typical exoplanet going around a star, then when it's in front of the star, the light from the star is cut back. And so you have a sort of a luminosity function that looks like this, where it drops off as the body is in front of the star and then goes back up again. So this tells us how big the star is, because we know enough about most stars to know how big they are. So it tells us how big the planet is, and it tells us what the orbital period of the planet is, and we start to get information from these transits. So in 1995, we had 1 exoplanet. Now in May 2020, the last time I looked, we had 4,266 confirmed exoplanets. These are confirmed. These are ones where there's been multiple observations. There are another few thousand where there's been one observation waiting for confirmation. And this has used this radial velocity method and the transit surveys. There are others. There are techniques called microlensing and direct detection. They don't produce quite as many observations. The main ones tend to be from transit surveys with some radial velocity. We also have a mission that's been launched called Gaia, which is doing astrometry on the stars around us. And that is expected, the results are beginning to come in now, is expected to find anything up to 10,000 new planets. So 4,200 exoplanets, these are in 3,000 systems, which means that there have to be about 700 multiple planet systems. What that means is if you take the transit, for example, that means you've got 2 black dots or 3 black dots going across the disk. Or with the radial velocity measure, your curve gets more complicated and you can extract more than one planet from it. And so you can graph how many of these things we got. So here we have a graph that just shows the masses of planets going out from 0 to 10 Jupiter masses and the number of planets we have. Now we started out here because we could find these Jupiter-sized ones very easily because they were so large. But what we're finding is as our measurements get better and better, we're finding more and more and more down this end. And in fact, we find the universe is dominated by smaller ones. These are the ones we're interested in because these are the rocky ones. These are the Earth-like ones. These are the ones where you might expect life to exist. You wouldn't expect life to exist on something like Jupiter, maybe, but you might expect them on these rocky ones. And we are finding more and more and more of these as our measurements get better. So where are these planets? Well, we can look locally and have a look and see what we have nearby. This is a map of all our target stars out to 14 light years. So we have, for example, the nearest planet, the nearest star, Proxima Centauri and Alpha Centauri. We know, for example, that Proxima Centauri has a small Earth-like planet going around it. This is only 4 light years away from us, our next door neighbor. But within this series here, this is a diagram that shows you 32 of the closest stars. Around those, 16 of them at least are known to have planets, and 8 of them have planets in the habitable zone, depending how you measure the habitable zone. So there's a lot of potential targets out there to look for signs that life might exist. We now have all these thousands of exoplanets, and what do we know? We have a whole list of ideas about these, a whole list of measurements of these. So we know that the lightest, for example, is only 2% of the Earth's mass. The heaviest is 30 Jovian masses. The shortest year is less than a day, a few hours. The longest year is 2,100 years, Ophiuchus 11b. Closest to the Earth, Proxima Centauri b. The furthest from the Earth, we have measurements of a planet around a star 8,500 parsecs away. So we have a lot of space that we're working in. So let's go back and look at this again. This is a transit. Okay, so behind the bright area is the star. The planet goes in front of it, and you can see that the disk tells you how big the planet is. You see how much light it cuts off. That tells you how big the planet is. But around this planet, you see the annulus. This is the atmosphere of the planet. And as it goes across in front of the star, the light from the star will shine through that annulus. And if you can look at that annulus at different wavelengths, then maybe there are different effects at different wavelengths, which tells us something about the annulus, tells us something about the atmosphere. And so we looked at that and say, so if we look at the spectrum, what does it tell us? And here is a confusogram that tells you something about the way that we do this work. And the first planet that we looked at, there was a star beautifully called HD 209458b, 209458. The planet was therefore called HD 209458b. And this was some of the first measurements taken on the spectrum of this. And this is in the Lyman alpha line. That fact's not important. What is important, if you look at the diagram on the left, which is the spectrum around, now Lyman alpha is affected by hydrogen. And we have 2 lines here, if you look at this. One of them is what the star looks like in the spectral region without the planet in front of it. The other line is what it looks like when the planet is in front of it. The difference is the effect of the atmosphere of the planet. And so the amount tells you what you've got there. It tells you you've got hydrogen around that around that planet and a large envelope. But if you compare the two sides of this, you also get the Doppler shift. You get the speed with which that gas is moving. And this tells you that that gas is coming towards us at a very large velocity. So you get essentially a model of what you see on the right here, which is that this planet, which is the size of Jupiter, has a gas cloud which is being boiled away and flung out from it. So it looks like an enormous comet. We have a planet the size of Jupiter with a tail like a comet away from that star. This is something that we can't see. The telescope would never have a resolution to see this from Earth, but we can deduce that from the simple measurements made on the spectrum of the difference between the star and the star plus planet. So can you take this even further? And it ends up, yes, we can. We can look at these atmospheres in more detail. We can take a bigger, longer spectrum. So here again, we have another one of these gas giants. It's easy to do these measurements with gas giants because they're large with large atmospheres. So look first at the black line. The black line with all the error bars is the data. This is in the infrared 1.2 to about 2 microns. This is the spectral data that we get from it, all these different frequencies. So it varies a lot. So what causes the variation? Is that to do with the gases in the atmosphere? Can we say what gases are? So we can start thinking, well, it looks a bit like some of the water vapor plots we have. So let's fit the water vapor to this at this temperature and pressures that we expect. And look, oh yes, it looks quite a lot like the original spectral picture. So some of that looks like it must be water vapor. We can refine it further. Let's try other gases. So we add in methane. Now the green line shows you water vapor and methane, and suddenly this plot's even better. We're getting nearer and nearer to what the original spectrum looked like. Let's add some carbon dioxide, and then you'll get some purple things around here where we're filling in even some of the gaps that the other two couldn't show. And it's a bit over the top. We can even try a bit of carbon monoxide. So suddenly we're now in a position that we can look at these gas giants and we can tell you what the atmospheres contain. But it's all very well doing the gas giants. As I say, they may not be as interesting when it comes to looking for life. What we'd like to do is to do the same thing with smaller planets. We'd like to do this with rocky planets, super Earths and things like that. So what's the chances that we can do that? Well, at the moment, we're restricted to the sort of telescopes that Amelie showed you, VLT, 8-meter telescopes or 4-meter telescopes. But coming soon, we're hoping to get high resolution spectroscopy from the ground where we can look not at gas giants, but super Earths. These are things that are 2 or 3 times the size of the Earth or Earth-sized planets. Coming soon, James Webb Space Telescope. You'll see how old the slide is because it was going to be launched in 2014 when they made this. I'm hoping it's not one of these things where it's always 2 years in the future, but it's supposed to go up next year. And if it does, then we will get high resolution spectroscopy for Jupiters and Neptunes around other stars. And it might even be able to detect super Earths and Earth-sized planets. We're also hoping to get the extremely large telescope, the AoT, and these 32-meter class telescopes should be able to directly detect exoplanets around other stars. There was a plan for something which I loved, which was called the OWI Owl, the overwhelmingly large telescope, but unfortunately, I don't think that's going anywhere at the moment. So anyway, that's where we are, and that's where we are, and that's where we're going. So the conclusions are, we are currently in a golden age of discovery. We now have 4,000 of these exoplanets. There'll be 10,000 when Gaia comes on stream properly. Already, we can tell you something about their sizes, their orbits, their temperatures, even the compositions of the atmospheres. And in the near future, as the telescopes get better and the resolutions get better, we might be able to tell you more about the surface textures, the seasonal variations, and the detailed atmospheric compositions. So we learn more and more and more about these, and we have thousands and thousands of potential planets in our list. So then the big question comes back again. If we're using this to look for life, whether we think life exists out there, is that enough information? If we have all that information about all those planets around all those stars out there, does that get us any nearer to answering that question? Have we found life elsewhere in the universe, or haven't we?
Well, thank you very much, Alan, on this tantalizing question. I think it's truly unbelievable that, you know, a few decades ago, we thought there were no exoplanets, and, you know, or that maybe there should be, but we hadn't found one, and now we have, you know, it's become common. It's quite crazy. So again, the chat is lagging a bit, but Chiara or Corentin, you have a question to start?
Yes. So Alan, you showed the image with the exoplanets around stars discovered so far, more or less. And you showed also that the exoplanet farthest away, it's like a few thousand parsecs from us. But to give an idea maybe to the people watching, so compared to the size of our galaxy, of the Milky Way, how large this area is? Because it looks like we have discovered exoplanets very far away, but then if we compare to the size of the galaxy, then...
Yeah, obviously it's easier to find the ones that are nearer. I mean, obviously, because, you know, your signal's bigger and all of the methods obviously work better near. But you do get these gravitational lensing experiments where basically you can have a galaxy which is lensing something behind it, or you can have a large area of a galaxy lensing. So there you can have things which are thousands of parsecs away, where you, I mean, I can't go into the technique, but basically if a star with a planet passes behind one of these lensing regions, then you can detect planets around it. And in fact, you know, some of these things are so far away that we'll only ever see them once, because they'll only ever pass behind that lensing region once. But you can see things outside the galaxy. And in fact, I think the 8,500 parsecs is outside our own galaxy. You should know better if you're an astronomer. I'm only a poor atmospheric physicist.
Okay, good one. So of course, very first question on the chat is, do you think it would be possible for habitable exoplanets to have living creatures? And, you know, would they be similar to the human race?
Well, I mean, that's of course one of the key questions, and it comes down to the fact that we use water as what we're looking for. You know, we assume that if we're going to find it, we're going to have water there. We look for regions that have liquid water. That's part of our parochial assumption that life is like us. You know, you have science fiction in the past where instead of using carbon as the building block, you use silicon. Whether that's actually possible or not, I think is debatable. But the question is, how does life come about? And if you have all the conditions, if you have a planet like ours with the right temperature, the right conditions, does life automatically come about? And that is one of the big questions. You know, that's partly why we're on Mars at the moment. Mars had conditions in the past very similar to Earth now. Did life come about on Mars then, or has it always been barren? It's we don't know, and these are areas of science which are going to keep us questioning for a long time, I think.
Yeah, we have another question from the chat. Is there a way to observationally detect the chemical composition of the internal part of the planets, of the exoplanets? Sorry.
Well, okay. It's a good question. It's a matter of how subtle you get with your observations. There are two sides of that. One is if you can find the chemical composition of the atmospheres, which you obviously can, then that tells you something about what created the atmospheres. So you can start conjecturing about the solid body that's underneath that created that atmosphere, and also about the history of the body, where that body came from, what the initial nebula was that created it. So you get some idea about it. But also some of the advanced techniques for doing these transit studies can actually look at how the planet varies in emission throughout its orbit. And so that might tell you that sort of on one part of the orbit, it's brighter than it is on another. So that might tell you about the difference between the front and the back of the planet. And so therefore you get some sort of geographical information about the geology of the surface and how some bits are different colors than others. But you might be able to do something latitudinally, tell like whether it's got ice caps. You might be able to tell something about the chemical composition of the body by the way it reflects the light. So it depends on how well our observations turn out. If we can make the observations with enough resolution and we're long enough, then yes, maybe we can start to tell something even about the surfaces. It's a bit more difficult to look inside. I mean, you can't even do that with most of the planets in our own solar system, but we can infer a lot.
So the next question is, so we are looking for other planets, but if an observer outside the solar system would look at us, what would they see? Would they be able to make the same measurements, or is Earth a difficult planet to characterize?
Well, they would have the same problem that we have, which is that from outside the solar system, telling about Jupiter is fairly easy because it's large and it's got a large atmosphere. They would need to make the same technological advances that we would to be able to get down to Earth-sized planets. They would need to be in a plane where the Earth passed in front of the sun, so that they could see the atmosphere from there. So if they're up and below the plane of the ecliptics, then they're not going to see a lot. But if they're in the right place and they have a powerful enough telescope, then they could start making discoveries about the Earth. And in fact, there have been people who've done studies of this. Carl Sagan, who used to do science presentations years ago, showed that as I think it was the Galileo probe passed Earth, it made measurements of the Earth's atmosphere and could tell you that it had oxygen and several other gases in the atmosphere. So then the question comes, is the presence of oxygen prove that there's life here? And you get questions about what do you need to know about a planet to know what's on the surface. So certainly from outside, you could tell some things about it. You could tell the Earth's atmosphere is oxygen, nitrogen, and a few other gases, and you could tell something about the average temperature of it. You could guess that liquid water would exist on the surface. But how much evidence do you need to draw conclusions from those? I mean, that's again, that's where your tipping edge of science is at the moment.
All right. Well, thank you very much for another great talk on, as you said, another hot topic of astronomy for the public. It's been a great evening, and we will soon stop here. Before we leave you, we can already announce the talk for next week. So next week on Astronomy on Tap, if you've heard the sentence or the expression that you're all made of stardust, well, next week we will talk about cosmic dust and how supernovas are formed, and so basically how stars die and explode. We are going to hear from Franziska Schmidt. So in 2 weeks, it's going to be a shorter event, as we will now move from a weekly show on YouTube, as the lockdown is going to continue. So you will have every week one talk and then a Q&A session. So it's a bit shorter, and it's probably more suited to the rhythm and then the attention span that we have on YouTube. So on this, we will just say goodbye and see you in 2 weeks. Bye.
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 Okay, I'll see you.